We are going to finish our study of limits with section 11.4, and we will be discussing limits at infinity. And by that I mean we're going to be looking at limits as x approaches positive infinity or as x approaches negative infinity. So let's first discuss the notation. So the notation, the limit as x approaches positive infinity for f of x equals L means as my x value gets, okay, if x is approaching positive infinity, then that means my x value is doing what? It's getting larger and larger. So as my x value gets larger and larger, my y value gets close to a number L, or close to the limit. So as x approaches positive infinity, my y value gets closer and closer to the limit. Let's look at the second bullet point. The notation, the limit as x approaches negative infinity of a function equals L means as my x value gets, okay, as x approaches negative infinity, my x value is not getting larger and larger, but it's getting smaller and smaller. So as my x value gets smaller and smaller, my y value is getting close to a number L, the limit. So first I would like for you to analyze, number one, function A and function B. And function A and function B have both been graphed over here for you to the right. So function A is 5 over 2x. Function B is the same, but you'll notice that A is asking for the limit as x approaches positive infinity, and B is asking for the limit as x approaches negative infinity. So I'm going to highlight and trace the function as x approaches positive infinity. So if x is going to positive infinity, I know that I need to be on the right-hand side. X is getting larger and larger and larger. X is at 10, and x will continue to get larger and larger and larger. I want you to take a guess at the limit. As x gets bigger and bigger and bigger, as it approaches positive infinity, what does it look like y is approaching? And then I'd like you to do the same thing for b. As x approaches negative infinity, or as x gets smaller and smaller and smaller, what does it look like y is approaching? Take a guess. If you said 0, you would be correct. Hopefully you have worked with rational functions enough to recognize that we would have a horizontal asymptote at 0, at y equals 0, based on the behavior of this function. So 1a and 1b, one is approaching an positive infinity, the other x is approaching negative infinity, but both have a limit of 0. 0 happens to be the horizontal asymptote of this function. Take a look at 2a and 2b. The function is graphed for you here on the right. I recognize that these are rational functions, and I'm finding the limit as x approaches positive infinity in a. So if I want x to approach positive infinity, if I start here in the middle, my x-coordinates are approaching 0, and now my x-coordinates are approaching 1, but if I stay here in the middle, my x-coordinates are never going to get close to positive infinity. So I'm going to skip over to the rightmost section of this rational function, and now I can see that x is getting larger and larger and larger, or approaching positive infinity. Take a guess for what you think the limit as x approaches positive infinity would be. Now let's look at x as x approaches negative infinity. Again, I could start in the middle and move towards negative infinity value for x, but my x doesn't get very close to negative infinity. It really is just my x is getting closer to -1. So I want to be on the leftmost portion of this rational function And now I can see that x is getting smaller and smaller and smaller as it approaches negative infinity. Take a guess at what you think the limit for 2a and 2b is. And if you said 2, you would be correct. You might see that that limit corresponds to this horizontal asymptote of 2. Let's look at 3a and 3b. Again, we have rational functions. One's approaching positive infinity, the other is approaching negative infinity. So in 3a, if I want to find where x approaches positive infinity, I could start on the left, but x really never gets closer to positive infinity than an x coordinate of -1. I could skip to the middle section of this rational function, but x never really gets closer to positive infinity than the number 2. But if I evaluate the rightmost section, I can see that as x gets closer and closer to positive infinity, something's happening to my limit. So place what you think the limit is on 3a. And then do the same for 3b. For 3b, because x is approaching negative infinity, I definitely want to be in the leftmost section of the function, and now x is approaching negative infinity. What's y approaching? So in 3a, as x approaches positive infinity, it looks like y is also approaching positive infinity. In 3b, as x approaches negative infinity, it looks like y is approaching negative infinity. So our limit is approaching positive infinity and negative infinity. However, we understand now that a y value, as y gets closer to positive or negative infinity, we are not approaching one unique y value. So we would say that for 3a and 3b, the limit does not exist. The limit does not exist. So what I'd like for you to do is to take a moment and analyze function 1, 2, 3. Compare their limits to the graph. Compare their limits to the graph of the function and see if you can determine a method with which to evaluate limits as x approaches positive infinity or negative infinity. So hopefully you recognized that the horizontal asymptote matches the limits. The horizontal asymptotes are matching our limits. And in 3a, we have no horizontal asymptote. So there is no horizontal asymptote that matches our limit. Our limit does not exist. Because we don't have that horizontal asymptote, we have unbounded behavior. So how do we know when our horizontal asymptotes will be 0 versus this value of 2 versus not having one at all? So let's review at the top of the second page. Early in the school year, we learned that to find horizontal asymptotes, we would look at the degree of the numerator and the degree of the denominator. We learned that if the function was bottom heavy, then our horizontal asymptote was 0. We learned if our degrees were the same, then our horizontal asymptote was the ratio of the leading coefficient. And then we learned there was no horizontal asymptote if the function was top heavy. And because limits as x approaches positive and negative infinity matches that, as long as you know whether the function is top heavy, number 1, a and b, the degree of the numerator was 0. The degree of the denominator was 1. This function was bottom heavy. Our horizontal asymptote was 0. Therefore, our limit was 0. In 2a and b, the degree of the numerator was 2 and the degree of the denominator was 2. Because the degrees are equivalent, then the ratio of the leading coefficients, 10 divided by 5 equals 2, was our horizontal asymptote and thus our limit. Lastly, number 3, the degree of the numerator was 3 and of the denominator was 2. Therefore, the function was top-heavy and there was no horizontal asymptote. Because that horizontal asymptote is missing, we have unbounded behavior and our limit does not exist. One more thing I want you to notice, because the asymptotes are horizontal, the limits as x approaches positive infinity and negative infinity will always be the same for each individual function. What I'd like for you to do is take a moment and let's go through these examples. I'm going to do the first example with you. Number 1, we want to evaluate the limit as x approaches positive infinity. Well, first of all, I see that I have 2 individual terms here. So one method with which to evaluate the limit is to first find a common denominator and combine these values. I know that my common denominator is x squared, so the numerator of the first term will become 4x squared minus the second term already contains the common denominator, so 4x squared minus 3. And now I can compare the degrees. The degree of the numerator is 2. The degree of the denominator is 2. Because the degrees are equivalent, then the limit is the ratio of the leading coefficients. With number 2, I want to show you a second option with which to evaluate the limit without having to find a common denominator. I can evaluate the limit of each individual term and then find the difference. Since this is subtraction, if this were addition, I would find the sum. So if I'm evaluating the limit of the first term, the limit as x approaches negative infinity for the function 4. This is 4 over 1. The degrees are equivalent. Therefore, my limit is the ratio of the leading coefficients, or 4 divided by 1 is 4. Minus, in the second function, the degree of the numerator is 0. The degree of the denominator is 2. This function is bottom heavy. Therefore, my limit is 0. And 4 minus 0 is 4. Pause the screencast and evaluate the limits for numbers 3, 4, and 5. All right, let's check. In number 3, the degrees are equivalent, so the limit is the ratio of the leading coefficients, or 2. In number 4, the degrees were equivalent, so the limit is the ratio of the leading coefficients, or -1. In number 5, the degrees were top-heavy, therefore the limit does not exist. In number 6, I want you to try the method that we used in example 1 or example 2. Remember, the method we used in example 2, you would evaluate the limit of each individual term, and that would keep you from having to calculate a common denominator in a new function. So in number 6, the degrees of the first fraction are the same, so I have the ratio of the leading coefficient plus the degrees of the second term the same, so again I have the ratio of the leading coefficient, and 1/2 plus 3 is 3.5, or 7/2. And then try the limit for number 7. And you can see that this function's degrees are top-heavy, therefore the limit does not exist. Remember, these rules are only valid as x approaches positive infinity or negative infinity.